Hello and welcome everybody to today's webinar on CoFlow and CoFlow-X, modern solutions for your integrated reservoir production modeling challenges. My name is Anjani Kumar. I'm the Vice President of Engineering Solution and Marketing at CMG. I'll be the moderator for today's session. With me, I have Varun Pathak. He's a staff reservoir simulation engineer at CMG who will be presenting today's webinar.
Hello, everyone.
Varun has over 12 years of industry experience working throughout India and Canada. Varun's experience includes fractured carbonate reservoirs, geomechanics, and unconventional reservoirs. He also holds a bachelor's and a master's degree in petroleum engineering from Indian School of Mines, India, and University of Alberta, Canada, respectively. Varun, has it been more than 5 years that you have been focusing on CoFlow and CoFlowX modeling IPSM workflows?
Yes, it's been about 5 years now.
So Varun has focused in the recent past modeling different proof of concept as well as real integrated production and reservoir modeling for assets around the world using CoFlow and CoFlowX. So he's going to share some of his experience and introduce CoFlow and CoFlowX to everybody. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. However, you may submit your questions at any time using the chat window on your screen. I'd also like to let you know that we will be posting a recorded version of this presentation on our website within the next 24 hours. You can use your CMGL username and a password to log in and access the material. Over to you, Varun.
Thank you for the introduction, Anjani. So hello, everyone. Here is my agenda for today. These are the things I would like to cover in my presentation today. I would like to introduce you to what integrated modeling means. Why do we need it? What is the point of doing that? I will present to you the solutions that CMG has to solve your integrated production systems modeling or IPSM challenges. There are two solutions that CMG has for you. One is CoFlow and the other one is CoFlowX. I'll present the details of both those software to you, and I'll showcase some demos and case studies while I'm presenting as well. I will talk about the offering of CoFlow and CoFlowX on the cloud, and I will finish up with my conclusions. So first of all, we need to understand, why do we need to do integration at all? Why do we need to incorporate production engineering, facilities engineering, and reservoir engineering all together? And the reason is that each of these disciplines cannot work in silo. We all need to pass information to each other and get the right data from one another, and then use that for making our production designs or reservoir recovery schemes. We need to transfer the right temperature, the right pressure, and the right fluid information to one another. And that is why we need to do integration. I'll explain this further in the next couple of slides. So the question to you is, are you considering cross-disciplinary data for your predictions and results? So if there is a production engineer and they are doing an analysis to figure out what is the rate and pressure at which a well can flow at, they would make a plot on the screen. This is a typical plot that is used in an analysis called Nodal analysis. It's a plot between the flowing wellbore pressure and rate. And you can see there is a green line and a purple line. The green line is the reservoir response that's coming from the reservoir, and it's called inflow performance relationship, IPR. The purple line is the lift performance that tells you how much your well can lift. So a production engineer would likely have a very accurate description of the purple line, but for the green line, they might be using a tank model or a simplistic correlation, which may or may not be completely accurate. The result of these two curves is the intersection point, and that is the operational point of your well. This is the rate at which the well will flow and the pressure at which the well will flow. On the other hand, there is a reservoir engineer who is doing his reservoir simulation and coming up with a more accurate green line, the IPR line. But he or she might be using a simpler assumption for the purple line now, which is the lift curve. They might be using a constant BHP, or they might be using some lift tables that were generated for a specific situation of the life of the reservoir. So the purple line might not be completely correct. And as a result, the operational point, which is the intersection of the two curves, may not be completely correct. The only way to get the right answers and have some confidence in your forecasts is by integrating the two. This is when you get your IPR curves from a physics-based model, such as reservoir simulation, and your purple line, which is your lift performance curve, should come from an actual well and facility model. And now you have a correct operating point, and this is what integration is all about. So to do the integration of production and reservoir, CMG offers implicit and explicit solution. Our implicit solution is CoFlow, and our explicit solution is CoFlowX. Depending on your situation, you would use either of the two software. If you want to have an implicit solution where all the solution, the reservoir equations, the well equations, the facility modeling, all of that you want to do in one single software, that's when you can use CoFlow. It solves traditional challenges faced by other tools that are in the market out there to do IPSM modeling. It has fully integrated uncertainty optimization using CMOST, where you can parameterize anything and really do a robust optimization. And it has multi-fidelity, which means you can simplify anything you want in the whole system of IPSM. So that's CoFlow for you. On the other side is CoFlowX, where you can just use a CoFlow system for your production modeling and couple existing IMEX and GEM models to it. It is very quick and easy, and you can leverage CMOST AI for a lot of uncertainty assessment and optimization. It is explicitly coupled, which means IMEX and GEM are talking to CoFlow in an explicit manner, and this leads to a very good performance. And of course, all of this is a single vendor solution for all your needs. So together, what CoFlow and CoFlowX achieve is that because we are in the CMG world, you have access to IMEX and GEM and CoFlow now on the reservoir side. And with that, you can model any recovery process that you can have in your reservoir. Now with CoFlow, we also can do production engineering, which is the right-hand side of this picture. You can do tubing completion design, artificial lift assessments, decline-based IPSM, facility debottlenecking, and network optimization. And the intersection of these two disciplines, reservoir and production, is what we can do now with the CoFlow and CoFlowX approach. Now you can have more confident reservoir forecasts, which are consistent with your production system. And your production design can also be a more robust design, and it will be based on actual reservoir behavior now. So to explain in more detail, I'll go into CoFlow for the next few minutes. So CoFlow is CMG's solution for integrated reservoir and production coupling. It's an integrated modeling environment where multiple users can collaborate with each other. CoFlow was started as a joint venture between CMG, Shell, and Petrobras, and the objectives are to get better engineering decisions, especially for the high stakes plays. And by doing that, we can reduce the cycle time from concept to field. We can encourage better collaboration between disciplines, and it's customizable software where you can very easily design workflows suitable for your own situation. And by doing all of this, ultimately you can accelerate and maximize your cash flows, and you can optimize your big investments in the field. We all know now that it's important to integrate reservoir production systems, but it is not always so easy. It can be time consuming if you're not using the right tools. Typically, it is done by using multiple tools which are made by different companies. So reservoir simulation is on a different tool, production engineering is on a different tool, and the users are generally siloed. The communication between the various disciplines and the various tools is oftentimes ineffective. There are data management issues where you have file and folder management and maintaining all these different infrastructures in one go. And there are issues with data consistency. For example, the fluid flowing from the reservoir simulator may not be exactly the same fluid that you are using in the production system. So there are issues with data consistency as well. CoFlow solves these challenges by integrating the whole system. Now you have a multi-user, multidisciplinary environment where all the users, as you can see on the picture, are working on the same database, sharing information between each other. It is a multi-fidelity tool. So one of the reservoir engineers is using a black oil fluid in their reservoir simulation. Another one is using a K-value fluid. And then geomechanics people are also integrated. They can use compaction tables or real geomechanics. Production people are also collaborated in the same system, where they can use the simple reservoir descriptions or use the full description coming in from the reservoir engineer. And to top it all off, we have integrated uncertainty optimization, where you can parameterize everything from the reservoir to the production facility using CMOST AI, and then leverage all the things that comes with CMOST AI. On top of that, CoFlow is an extensible software where you can write your proprietary plugins for your specific scenarios and make it work with CoFlow. So I will explain more through a case study in CoFlow. This is a case study where we made a model for a pre-salt Brazil reservoir. There are two reservoirs in the system, a carbonate reservoir and a sandstone reservoir. The carbonate you can see on the right hand side is the shallower reservoir, which is appearing in the blue color for permeability. The average permeability is about 500 millidarcy there. It's heterogeneous reservoirs with multiple facies. And then the bottom reservoir is the sandstone reservoir, which is a more homogeneous reservoir with a better permeability. And together, these two reservoirs have been developed using an FPSO-based development, which has a production limit of 150,000 barrels per day. And both these reservoirs have different fluid systems and different facilities as well. So in terms of the fluid, you have the choice of using any fluid type in any of the reservoirs. So in carbonate, I can use EOS, K-value, or black oil fluid, and same thing in sandstone. Then I take this production down to the carbonate and sandstone networks, as you can see. So carbonate fluid goes to carbonate network and sandstone fluid goes to sandstone network. And again, you have choice of using any fluid type. In fact, you can use a black oil fluid in the reservoir and an EOS fluid in the facility if you want, or vice versa. Then this fluid combines at the FPSO level, which is the red circle here. There, the two fluid systems are mixing with each other, blending with each other, and some processing is happening there. So there we have to use a model of fluid that combines the two fluid systems, and CoFlow does that automatically for you. So on the right hand side, I have the fluid description of the three fluid streams that are flowing in this whole system. The red line is the sandstone EOS fluid. The dark blue line is the carbonate EOS fluid. And the combination of the two fluid systems is the green line, that is the blend of the two fluids. And this green line is going to be constructed by CoFlow in real time automatically, and you won't have to worry about how these two fluid streams are mixing with each other and how do I use the right properties for modeling my FPSO. Then the next thing you can do in CoFlow is well design and nodal analysis. In this study, we did intricate wellbore design by doing dynamic nodal analysis. In this picture on the right hand side, it's a picture between bottom hole pressure and liquid rate, and that is coming from CoFlow's nodal analysis, where we are testing the effect of different wellhead pressures or top hole pressures and different tubing sizes. So the black dotted line is the IPR curve coming from the reservoir, and all the other lines are lift curves from the production side. So you can see that if I use a lower top hole or wellhead pressure, I can have a significantly higher production from this well. And similarly, if I change the tubing sizes, so you can see there are two groupings. The top groupings are for the top hole pressure of 25,000, and the bottom groupings are for the top hole pressure of 21,000. And within each grouping, there are three curves. They are corresponding to three different tubing sizes. So you can do a sensitivity and figure out what is your best tubing size that you can use in this development. Then you can do the facility design in CoFlow. In this particular study, we have carbonate wells flowing into carbonate facility only, and sandstone wells flowing into sandstone facility only. From the carbonate facility, what we have done is we have a subsea gathering center. There are short pipes that are taking the flow to subsea gathering center, and then there is a liquid riser that takes the flow all the way to the FPSO. On the bottom side, the sandstone wells, which have bigger productivity, they flow into their individual pipes, but these pipes are actually risers that are taking the fluid all the way to the FPSO directly. So 7 sandstone risers and 1 carbonate riser in this development. So using CoFlow, you can identify bottlenecking equipment. For example, the pipe S6 here is a bottlenecking pipe, and you can try to do some debottlenecking by using a different pipe size and things like that. You can also do a robust design by incorporating geological uncertainty within your production design. So now I'm going to go to my CoFlow demo. And here is my CoFlow model, the two reservoir system that you see. The shallow reservoir is the carbonate reservoir, and the deep reservoir is the sandstone reservoir. So this is CoFlow interface for you. You can see, I can start from the left-hand side. You can see there are multiple users collaborating on this study. I have my asset study, and then there is this user, the name is demo. And then there are two more team members, Fred and Jane. I can see what Fred is doing, and I can see what Jane is doing, and I can grab their information from their data that has been checked into this database. So whenever you are working in CoFlow and you're happy with what you're doing, you can check in your results, and your team members can then see the results. And it doesn't matter where the team members are. Fred can be in South America and Jane can be in Europe, and I can just work together with them very easily. I can also give permissions to various people to just view the studies or write permissions and so on. So first thing you see in CoFlow is your geology. You've gotten the geological model and everything is set up correctly. And then you go and design your fluids. In terms of fluid, CoFlow can handle every single fluid system. You can have black oil systems, K-value system, or equation of state systems. In this case, Fred has done some work on fluids. So you can see he has designed the black oil fluid system, the EOS fluids, and the combination of the two. I got that information from Fred. So now I have a carbonate fluid described in black oil format as well as compositional format. And same thing for the sandstone fluid. And then I have created blends of the two fluids, the carbonate and sandstone black oil blend and the carbonate and sandstone EOS blend. And then I can go and look at the quality of my blends. So here is my carbonate EOS fluids PT phase envelope, the sandstone EOS fluid PT phase envelope. And if they were to mix in a 50-50 ratio, this is how the combined fluid would look like, the green line that appears. And this green line will be managed by CoFlow in real time automatically in the facilities, depending on what ratio the two fluid streams are coming into the facility. Then I go ahead and do my reservoir engineering. I set up my reservoir model. And one good thing about CoFlow is you can simplify the reservoir model or you can use it at the full resolution. So you can use a discrete reservoir or you can use tank and decline curves. Or you can take the base refined model coming from Geologist and upscale it within CoFlow. So here you can see I have upscaled my reservoir everywhere except the area around the well has been upscaled. So central area is not upscaled, but area away from the reservoirs, away from the wells has been upscaled. And then I can go ahead and do geomechanical modeling, which is compaction tables or full geomechanics, and then set up my wells. So my wells can be described in all their details. I go in and I specify the type of wells and where they're located and other properties in the wells as well. Here, one thing that would stand out is this table at the bottom. This is ambient temperature table. That's the temperature outside of the well, below the sea floor. So this gives me ability to do a correct modeling of temperature losses, which is very critical for offshore environment. Then I can set up any equipment in the wellbore as I want. So in this well, you can see there are tubings and there are perforations. Below the tubing, I also can specify any artificial lift, for example, gas lift valve or a pump. In this study, we had found that the natural lift along with re-injection of gas is better than putting artificial lift, and that is why you only see tubings and perforations. In terms of the tubing size, the size chosen is 6 inches, and that is done based on nodal analysis. So I'll show you that next. So that was done by grabbing the carbonate reservoir model from Jane and then running nodal analysis on that. So you go to nodal analysis and you generate one and evaluate tubing sizes and top hole pressures. So in this analysis, the blue line that's appearing up there is your IPR curve coming from the reservoir, and the green and red lines are the two lift curves for two different top hole pressures, but for the same tubing size. So that tells you that if you use a lower top hole pressure, you can increase the production from about 700 meter cubes per day to about 1700 meter cubes per day.
And Varun, the IPR curve can come actually from either a decline curve or from the actual simulation results, correct?
Absolutely, absolutely. So it comes from either your discrete reservoir curve, discrete reservoir results, or from your tank model and decline curves. So continuing along, if I pick just one top hole pressure and I want to evaluate the different tubing sizes, you can see that if I use a bigger tubing size, I can produce more. So it's evident from this picture now. I can look at the actual operating points, and you can see where the operating points, that is the intersection between the two curves, is. If you are just interested in operating points, you can go here and look at what the operating points can be. So here I've grouped everything on one plot. The 21,000 left, the y-axis is liquid rate and the x-axis is the top hole pressure. And you can see when the top hole pressure is small, you have a big rate, and when the top hole pressure is big, you have small rate, which is intuitive. But within, if you just pick one top hole pressure, for example, 21,000, you can see that the production can increase from about 1700 to maybe 1850 using a 1 inch bigger, like 6-inch tubing instead of 5-inch tubing. But going from 6-inch to 7-inch doesn't give you that much of an increment, and 7-inch can be much more expensive than 6-inch. So we decided that we will go with a 6-inch tubing for our base design. You can also look at the contributions of pressure coming from various sources. So this picture shows you that most of your pressure drop is coming from hydrostatic, because these are mostly vertical wells, and some of the pressure drop is coming from friction. So based on this, we conclude that we will be using 6-inch tubings for all our wells. Continuing on to the facilities, we have the Carbonate facility, where you have individual wells flowing into small pipes and then subsea gathering center, and then the fluid goes into a liquid riser. So let's look at the riser. The riser here is a J-shaped pipe, and again, you're doing all the pressure drop calculations and all the temperature drop calculations right from the sea floor to the FPSO. So the water depth is about 2.5 kilometers, and this particular well is located about 700 meter horizontal distance from the FPSO. At any segment in the pipe, you can change your correlation and use a different correlation if you want. There is a choice of correlations available to you in CoFlow. On the sandstone fluid, each pipe taking the fluid from the well to the FPSO is a riser. And the shape is a bit different because it's a longer riser, and you have to account for the weight of the pipe that's applied onto the FPSO. So we use a lazy wave profile. And once again, all the pressure drop calculation and all the temperature drop calculations have been done. So one thing to notice is the fluid model being used in sandstone facility is sandstone fluid, and in the carbonate facility is the carbonate fluid. So in the integrated facility, that is the FPSO, the fluid is the blend of the two fluid systems. And that blend, the properties of this blend is going to be calculated in real time by CoFlow, and it will be automatic. In the FPSO, what we are doing is we have a single stage separation. We have a constraint of production, and we are separating the water and oil and then sending the gas to a distributor, where some gas goes to sales and fuel and flare, and remaining gas is sent to injection wells using compressors. Okay, so that is what we are doing in this study, and we are doing an optimization as well. So in this particular study, we want to optimize our production that's coming in at the FPSO. So I'm trying to maximize the liquid production or the oil production at the FPSO using a decision variable on my wells. So I'm going to produce my wells at a particular rate that is determined by the optimizer, such that I can elongate the life of the well and life of the field and just maximize the production to the maximum capacity of the FPSO. So this optimization is going to be done as often as I want. I can do it every month, I can do it every 6 months. And then we can look at the results within CoFlow as well. So let's look at the geological model of carbonate, and you can see that it's low permeability system, and you can see the refinements on the grid here, and dynamic model, which is after upscaling. You can see that it's been upscaled in the areas away from the wells. And you can see that the pressure drop is quite significant around the wells of Carbonate, so that's why we are doing a gas reinjection scheme. In terms of results, you can look at the oil rate coming from the two facilities. So the Carbonate facility is only producing about 5 to 6,000 meter cubes per day, and Sandstone facility is producing about 18,000 meter cubes per day. So most of the production is coming from Sandstone and some from Carbonate. So maybe 30% is from Carbonate. You can look at some flow assurance properties. So you can create a profile of the temperature inside your Carbonate riser. And that is very important because you don't want to get into low temperature systems where hydrates and asphaltenes can deposit. So I'm going to plot temperature inside this pipe at 3 different times, one at the beginning, one sometime in the middle of the simulation, and one towards the end. And CoFlow will create this plot for you, and then you can evaluate how the temperature is varying inside the pipe. So on the x-axis is the length of the pipe, on the y-axis is temperature inside the pipe. And you can see we begin at a fairly good temperature, about 52 degrees Celsius at the sea floor. So remember, the wellhead is at the sea floor. It's a wet wellhead. And by the time 2,500 meters are done, or 3,000 meters are done, which is at the exit of the FPSO, the temperature has dropped to 34 degrees. So that goes on for first couple of years. But in the 4th year, we can see the temperature has dropped quite a bit at the FPSO. So it's 22 degrees now at the FPSO, and that's a little cool, and it can lead to asphaltene and wax problems. So basically, CoFlow can use these results to do some action and prevent the temperature from dropping too much. So that is all you would do in CoFlow, and then our base case has been created now. So I'll go back to my presentation, but before that.
Before Varun goes into the next session, I like to ask a question from the audience. Soon you'll see a question pop up on your screen, and you can select one of those options and click respond. So the question is, what are your main challenges while doing IPSM modeling? The options are data consistency between reservoir and production models, difficulty in coupling reservoir and production models, lack and ease of data exchange across disciplines, and all of the above. We'll give a few seconds for everybody to respond. And the responses are coming right here. Around 18% of the people who responded believe that data consistency between reservoir and production models are an issue. Around 20% says coupling is difficult between reservoir and production modeling tools. 15% around say lack and ease of data exchange, and majority say it's all of the above. And I agree. I mean, depending on the tools that you're using and depending on consistent data usage between different disciplines, and one of the most important ones are the fluid consistency between used in between the reservoir models as well as the network models, or for the well analysis models. There are certain assumptions in different tools that are made while designing those tools, and consistency becomes an issue when you transfer data from one tool to the next. And since CoFlow is designed from scratch, keeping in mind IPSM workflow, all your reservoir related equations and surface network and well related equations are solved together fully implicitly and simultaneously. So there is no coupling as such required between the tools. It's one single system which is solved simultaneously, and hence there is no consistency issues that you would see in a normal traditional coupling approach for doing an IPSM. So I hope that this new workflow will eliminate a lot of these challenges that users face in doing a coupled IPSM workflow. Okay, back to you, Varun.
Okay, thank you, Anjani. So the next thing is we designed our base model. Now, how do we optimize our facility so that it works for all uncertainties that can happen in your reservoir? So it's a 4-step process. what we'll do is we'll first design our base case, which we have done. We'll pick our well design, our well locations, and our facility design. And then we identify what are the things which we can change. So for example, maybe you can change the tubing size, but there is no control that on the artificial lift. You don't have a choice. It can be happening in the field. So whatever are your main decision variables, you identify them. Then you test your design, your base design under geological uncertainty. You do your IPSM simulations under the uncertainty and identify if your base design was actually optimal or not. And if not, then you identify how much uncertainty is there and if you can update your production system design. So in this study, we continued our work into a SPE paper where we took the geology and we got a bunch of realizations from the geologist. So I'm showing 3 here on the picture on the left. There is a P10 realization, a P50, and a P90. And corresponding to each of the realizations, I have a scheme of the well locations. So scheme A corresponds to the best recovery that we can get from the P10 realization. Scheme B is for P50 and scheme C is for P90. But those, we can only pick one when we go into the field. So which one do we pick? So that's another question to ask. Then the tubing ID and tubing insulation, we just try to identify that using nodal analysis and we picked a 6-inch tubing size. But is that optimal for all the uncertainties that there are? Do we need artificial lift? Should we try using a pump or should we just leave the wells to flow naturally? Then on the facility side, the carbonate riser size can be uncertain. We can try different riser sizes for different geological realizations and see which one is the best. And same thing goes for the sandstone riser size. And lastly, the FPSO separator pressure has been picked as a starting point for one realization. But does it work for all the realizations or not? So we can do all these analyses in CoFlow. And that is my next demo. So what I can do in CoFlow is I can very easily bring in geological realizations that are coming from geologists and set them up in CoFlow and then set up my reservoir model accordingly. And then within the wells, I can parameterize the entire reservoir. So instead of associating the well with realization 1, I can do it to realization 2. So I'll show you example of carbonate well 10 here. You can see that this particular perforation corresponds to the carbonate P90 realization. And at the same time, all the wells in carbonate are corresponding to carbonate P90 realization. But I can parameterize the whole reservoir. And I can say that I may not be using the P90 realization. I may be using P10 or P30 or P50 or P70 or P90. I gave them equal weightings because I don't know which one is better. But if you have some distribution which you want to use, you can use that just like you would do it in CMOST. So my entire reservoir is a parameter and all the wells would be using either one or the other reservoirs when we do optimization analysis in CMOST. Similarly, my tubing size is a variable that I can test. I have a choice of using 6-inch, 5-inch, or 7-inch tubing sizes. Then I go ahead into my facilities and I parameterize my entire facility as well. So in case of the carbonate facility, I can see that I'm going to make either one of the equipments as a parameter, or I can parameterize the whole system. I am not forced to use a single gathering center facility, for example. I can completely change my facility and use that as a parameter. In this case, I have parameterized my liquid riser size. So I'm using 6-inch carbonate riser, 8-inch carbonate riser, and 10-inch riser. And I can specify the whole facility diagram as a parameter. So here you can see that I'm using a different liquid riser size for each realization. This is the 8-inch that's coming up. And you can see that it's 8-inch diameter here. So we have 3 different settings for carbonate riser that we are testing out. And with that, I make all my parameters and then I can just go into CMOST and do my CMOST analysis. So CMOST will know what my properties from the facility are. CMOST would know what my parameters are. And I have set up 2 objective functions, cumulative oil from carbonate and cumulative oil total. and I'm trying to maximize it using CMOST. And I'll present their results in my slides next. So what we found, the first and the main parameter was the tubing size in carbonates. So for all the three schemes of wells, scheme A, scheme B, and scheme C, I plotted carbonate reservoir cumulative oil production in CMOST and plotted and make a cross plot versus different tubing sizes. So the first set of dots you see is for diameter 6-inch. The second set is for diameter of 5-inch, and the third set of diameter of 7-inch. And in all the three schemes, you can see that 5-inch is on an average giving you a better result than either 6 or 7-inch tubings. Now remember, in nodal analysis, we concluded that 6-inch tubing is the best tubing size to use. But when you run a fully coupled integrated system with uncertainty included in it, you realize that you would have made a mistake if you would have gone in with a 6-inch tubing size. So we changed our design, and now we are going to go with the 5-inch tubing size instead of 6-inch. On top of that, it could be cheaper as well. So it's a double benefit. The next thing we evaluated was the effect of using artificial lift. So we had a choice of two pump designs from two manufacturers. So there is pump 1 that's here, and there's pump 2 that's here. So again on the y-axis we have cumulative oil production from carbonate, and on the x-axis is the three different groupings for pump 1, pump 2, and natural lift. And we had designed our base case without using natural lift, but while using pump 1 we realized we can increase the production significantly, and also with pump 2, but pump 1 was better than pump 2. And then we can now decide whether we want to go with a pump in the wells or we want to keep going with natural lift. The data is in front of us. Logistical issues may have to be addressed, and we'll address it separately. The third thing was the effect of carbonate riser size. In the base design, the carbonate riser was picked as a 6-inch riser, and you can see that if I was using a 6-inch riser, my production will be quite low. If I would increase the riser size to 10-inch, it increases production, but it's still not optimal. But using an 8-inch riser was the best design, and that came from CMOST as well. So we changed our design to be using an 8-inch riser. And then lastly, we want to look at the effect of sandstone wells riser size. So here our base design was 6-inch, and after doing all the uncertainty assessment, we realized that 6-inch is still a decent pick for the risers of sandstone. So we continued to go with a 6-inch riser in sandstone. So with that, we have done a full analysis of our system. A traditional system, you would be doing reservoir engineering on one tool, production engineering on second tool, geomechanics on a third tool, and uncertainty optimization would be completely decoupled from the system on a different tool. And there would not be any feedback going from reservoir into production or from production into reservoir. We would be just flowing information one way. There's lack of communication. Now, with the modern solution of CoFlow, we have coupled everything together. The reservoir models can be done in a different fluid systems. Geomechanics and production engineering can be done on the same system as well. Everyone is contributing data to the same database, and we have integrated the uncertainty and optimization all together with CMOST, end-to-end uncertainty assessment optimization.
So at this time, I'll like to ask another question to the audience, and similarly, a question will pop up on your screen. The question is, what process can you use integrated production systems modeling for? And some of the options that we can think of and are on the screen is tubing selection, artificial lift design for unconventional reservoirs, because you see a lot of flow assurance and lift issues in those kind of reservoirs, slugging effects and things like that. Production and injection optimization for miscible EOR processes, compressor design for gas fields, or any of the network facilities design, or all of the above. So looking at the responses here, it seems that a lot of people, 1/4 of the people actually do a lot of analysis related to tubing design and wellbore design, artificial lift design. So nodal analysis and lift design is very important for a lot of people. which is very, very intuitive because the production engineers and those set of engineers focus on the wellbore and flow assurance part of things. Around 70% actually say all of the above, which is again in line with the workflow that we are proposing, is that the entire system should be coupled together and looked into as a whole for the entire asset, so that you can maximize the deliverability, keeping in mind the constraints that are in the reservoir as well as in the network, and everything is handled together so that you can debottleneck the entire asset production system together. So back to you, Varun.
Okay, thank you everyone for their responses. Now I'll go ahead to our next system, and that's CoFlowX. So far we talked about CoFlow, and now the next few minutes will be devoted to CoFlowX. So what is CoFlowX? CoFlowX is CMG's second solution to your IPSM problems. Now you can couple CoFlow production engineering system, the wells and facilities of CoFlow, to existing models of IMEX and GEM. And the coupling tool is CoFlowX. So CoFlowX provides an explicit coupling between IMEX GEM and CoFlow. And there is no limit on how many IMEX and GEM models you can couple to CoFlow. By doing that, the benefit is that production engineer can enjoy all the tools of CoFlow in terms of wells and facilities, and the reservoir engineer can keep using the CMG software, the CMG simulators that they love. The benefits of using CoFlowX is that you leverage the power of industry's leading simulators, IMEX and GEM, for the best performance in simulation that you can get. And you can model any complex recovery process, unconventionals, chemical EOR, natural fractures, geochemistry, anything that you can model in IMEX and GEM. And then you can couple CoFlow, which is the main benefit. You can couple the production engineering system, and you can also leverage the power of other CMG software like Builder and CMOS AI. So you can do all of these things using CoFlowX. The concept how CoFlowX works is there is a communication between IMEX GEM and CoFlow, and this communication is handled by CoFlowX. So after every certain amount of time, which is called handshaking time or the coupling time between reservoir and production, at the coupling time, there will be information that will be passed from reservoir simulators to CoFlow. And this information is on the green in the right side. That information is IPR curves, the mole fractions coming from production wells, the drawdowns, the reference phases, and a suggestion for the next coupling time. Then CoFlow does its calculations, the wellbore calculations, the facility calculations, and it identifies the operational constraints, and then it transfers some information back to IMEX and GEM. The information that is transferred back is on the left-hand side. So it transfers the well constraints, the constraints at which the wells can actually flow at, depending on the facility limits and the well limits. It transfers the injection fluid compositions back to reservoir simulators, the injection temperatures, and another suggestion for the next coupling or handshaking time. And CoFlowX is very smart in identifying the next suitable coupling time. It looks at the user-defined handshaking frequency, the picture on the left side, that's coming from CoFlowX. The picture in the middle is showing the suggestion of this coupling or handshaking time made by IMEX and GEM, depending on the events happening during the simulation. And the picture on the right is showing the suggested handshaking time by CoFlow, depending upon the events that are happening inside CoFlow, inside the production system. So you have events happening in reservoirs, events happening in wells, events happening in facilities, and then there is a setting by the user. And CoFlowX goes and picks the best suitable setting for the next handshaking time by picking the minimum of these numbers. And these numbers can actually be dynamically changing. And CoFlowX will go and smartly pick the best number for handshaking so that your results are not compromised. And I'll repeat the same case study in CoFlowX now. The same facility diagram that you saw a little while ago, the Carbonate facility, the Sandstone facility, and then the combination of the two, which is the FPSO, where the fluids are blending and some gas is sent to flare or sails and some gas is reinjected into carbonate reservoir. But this time I'll change the reservoir system from CoFlow to GEM. So two different EOS systems are going to flow into the facility, and the blend of the two will be used for our FPSO. So that's my next demo, and I'll go to CoFlowX for that. So this is CoFlowX's interface, very user-friendly interface. CoFlowX is the coupling between surface network that's in CoFlow and reservoir models that has not been set up right now. So I'll be doing that. Very easily, you can pick your surface network properties. We have already picked my surface network, and CoFlowX has identified the wells automatically and identified which wells are injectors and which are producers. But they are not yet coupled to any reservoir wells because the reservoir models have not been added yet. So next thing we'll do is we'll add some reservoir models. So I'll go here and I'll add two reservoir models, the Carbonate reservoir, which is in GEM, and the Sandstone reservoir, which is also in GEM. I can just select both of them and couple them into my system. Very quickly, it will get all the information it needs. And automatically, you saw if the well names were matching, it couples the well names of the reservoir to the well names of CoFlow very easily. And if I change something in my reservoir, I can go and add new wells or define something new in my reservoir. Then CoFlowX can identify that also very easily. In the next step, I'll show you that. So let's say I go and rename the wells, rename the reservoirs. So one is Carbonate and one is Sandstone. Then I can go to the well coupling tab. The couplings are still present just the same way. And I can then submit my reservoirs on different number of processors on different computers. So I can pick one reservoir which is maybe easier to solve on 2 processors and the other one on 16 processors. It depends on how much computing power you have, and this will run just like you have set it up here. And you can pick up whatever cluster computers or local machines that you want to use. Then you just go into the engine and you literally pick the starting time and ending time for your coupling. You may not want to do it throughout. You may want to do it for only the forecast or only for a few years, and you can pick that, and CoFlowX will take care of the rest. You can pick up a frequency, how often you want to do coupling. Here I'm saying that at the max, I want to do it every 2 months, but maybe I want to do it more frequently than that, and that will be determined by my events happening in reservoir and production side. And then I just click on start and we start running CoFlowX. So I already have run this case and I have results from it right here. So when you start running your case in CoFlowX, it starts transferring this information which I was showing in the slide earlier. So I have Carbonate well 3. So let's look at this one well. At time 0, I'm passing some IPR information, which is the 2 curves at the bottom. The left-hand side curve is for water and oil IPRs, and the right-hand side curve is for the gas IPR, because predominantly liquid wells are different from predominantly gas wells. So we define different IPRs for the two of them. So my IPR at the beginning is here, and the intersection point of IPR and VLP is this star that I've highlighted. And as time goes by, my IPR keeps changing, and CoFlowX makes sure that the right IPR is transferred from GEM over to CoFlow. And on the other side, CoFlow is transferring the active constraint, the rate at which the well can flow at, to GEM, and GEM takes care of that and uses that for the next time stepping. So I can go in CoFlow and look at my results from this simulation as well. If I want to look at something specific for facilities, I can go in here and I can go and look at, okay, how much was the flow coming from the Sandstone and the Carbonate reservoirs? And this is a different model than the one I showed you before. So it's flowing 26,000 meter cubes from Sandstone and 6,000 from the Carbonate. And once again, I can go and look at any network properties. So I can look at Carbonate facility and a network object from this. I can pick up anything here, network, or maybe I look at the integrated facility, maybe that's better, and look at the gathering center and look at the temperature coming out of this throughout the simulation life. So you can see at the beginning, I'm coming at about 94 degrees. Towards the end, I'm about 90 degrees. So that's good enough. Hot fluid is coming in and mixing it in the FPSO. So I can evaluate whatever I want. I can do the same analysis I did in the previous study, but this time using CoFlowX. So with that, I finish my introduction of CoFlowX, and I go to my next topic. Well, first of all, I'll summarize CoFlowX for you. So CoFlowX, as you saw, it's a modern user interface, and you can couple reservoir and production models very easily. Typically, this is done by using tedious scripts, which only a few people understand in traditional tools. And now with CoFlowX, you don't need any scripts. It's going to do everything for you automatically. It is very easy to use. You don't need to do any changes in your data set. You can just bring in your original IMX and GEM data sets. No need to remove the well and recurrent section. No need to remove any triggers. No need to do anything at all. It's a smart software. It has automatic well coupling, and it intelligently selects the right coupling time. And there is no limit on how many reservoirs you want to use. You can use 10 IMX, 5 GEM, and any kind of combination, like 5 IMX, 20 GEM models, whatever you want. There is no limit at all. Now I come to my next topic, that is the offering of CoFlow and CoFlowX on the cloud. So you can, all our CMG software is available on leading cloud providers in the world. And by doing that, all you need is a computer with an internet connection, and you can connect to any of our software. And that includes CoFlow and CoFlowX now. The benefits to you are that it's an instantly scalable system, and the hardware is very flexible. So you don't have to go and buy expensive computers, and still you can use the most advanced computers that are there in the world on the leading cloud providers. You don't have to buy any hardware, as I said. All our latest software is always available on the cloud. So you have the assurance that you have access to the latest versions of all the software. The availability is immediate. There is no queuing up required for a large number of runs. So you can run a CMOS study which would require 200-300 jobs to be run, and very easily you can scale it up on the cloud. The access is instant, and it's available 24/7 so that you can fulfill your projects on time. And I want to show you how easy it is to use CoFlow and CoFlowX on the cloud. So here is my login screen for CoFlow and CoFlowX. You have to register to the cloud provider, and then you get a username and password, which I have, and then you open and you can access CoFlow. I've already logged into the system, and you can see the study I showed you earlier, the same look and feel of CoFlow as you would have in general, as if you were running on your own desktop. And the same thing, you run the cases, you analyze the results, you do whatever you want. So there is no difference in running CoFlow on your desktop or your laptop versus running CoFlow on the cloud. You get the exactly same experience. So with that, I come to the slide that shows you the deployments of CoFlow. We have deployed CoFlow in many different locations across the world for different companies. And there's a cluster that's there in various regions. There's multiple applications of CoFlow going on in the Gulf of Mexico. You can see here, offshore Africa, Nigeria, Angola. You can see the cluster here, and then the North Sea, and some applications in offshore Australia for gas. But we also have deployed CoFlow for several onshore locations, especially in South America and in the Middle East. So CoFlow has already been out there, and people have been using it for making business decisions for the past year or so. The bottom line is where I conclude my presentation. What I showed you is CoFlow and CoFlowX, and using these two tools, you can get all your IPSM needs met with a single solution, single software solution. You can model any recovery mechanism in your reservoirs, and you can do any kind of production design optimization for the production side of things. Now you can solve complex problems in a new way. You have a choice of using implicit or explicit solution, and either ways, it's a multi-user, multidisciplinary collaboration that is not present in any other tool. You can solve problems that we previously could not. An end-to-end uncertainty assessment and optimization is something which we have been aspiring to achieve, but haven't been quite able to achieve in traditional ways of IPSM solutions, but now you can do it. It has multiple fidelity levels at every component of integration. So you can pick and choose what fidelity you want to use for a particular component of IPSM and make faster decisions for your asset. And a complete fluid consistency, so you can be assured that the fluid coming in from the reservoir is the same fluid that is being used in the wells and facilities, and there is no inconsistency. As a result of all these things, it provides you a platform to reduce your risk and improve your return on investment, because now you have full collaboration and data consistency, which can lead to reliable forecasts. And with the CoFlow availability on the cloud, you don't have to make investment in your hardware. You can do it quite easily with the comfort of your internet connection. So with that, I finish my presentation, and over to you, Anjani.
Thank you, Varun. We will now take up questions. If you have any questions and have not already submitted it on the screen, you can do so now using the chat window. I already see there are a bunch of questions in here, and I'll try to take all of them, time permitting, but we'll go one by one. The first question is from George Ramos, and the question is, talking about IPR curve using CoFlow or CoFlowX, are you able to calculate the average pressure in the well drainage area? Now, I'll take up that question. Actually, since CoFlow uses the reservoir simulation models, even CoFlowX, it has access to the real-time drainage radius around each of the producing wells. So it intelligently allows CoFlow to actually take on the drainage radius and use that information in the nodal analysis calculations. Traditionally, in a decline curve of situation, users have to input an approximate drainage radius that may not be that accurate. But since CoFlow has access to the pressure profiles around the injector as well as the drainage radius, it uses the correct drainage radius for the calculations. The next question is from Chad, and the question is, what is the tool for modeling flow in the well?
So the answer to that it's CoFlow. CoFlow is the well modeling software, with whether you are using CoFlow or CoFlowX, and it takes care of all the completions that you want to set up in a well, smart completions, artificial lift, anything like that, that is done through CoFlow.
The next question is from Govin, and the question is, can you show the application of multi-fidelity solution for reservoir simulation? I think you already, maybe the question was before you showed the demo.
Yeah. So yes, I mean, Anjani got the point correctly. So I showed the option to use a refined discretized reservoir model or upscaled model, which is two different fidelities, and also there is an option to use decline curve or tank models for reservoir simulation, for mimicking a reservoir simulation model. So all of that is in CoFlow.
Yeah, I mean, if you have built in a decline curve for a particular reservoir and you also have a discretized reservoir for the same reservoir, then you can quickly flip by clicking a button to use one or the other in the CoFlow interface. The next question is from Govin again, and the question is, does it have a steady state simulation on production side, or a transient flow can be monitored?
So the answer to that is it's a steady state simulation. All the IPSM tools typically use steady state simulation on the production side.
The other question is from Calvin, and the question is, for well design, do you have packers, gas lift valves, and other downhole ICDs?
The answer is yes. All the things that you have asked, it's there in the wellbore design: ICDs, smart completions, packers.
Let's look at the other question from Murtaza, and the question is, can the system be used for real-time? No, I read the wrong question actually. The question is, in robust optimization example, you have different sets of control parameters, that is tubing size, artificial lift, risers. What happens to other control parameters when you are optimizing a particular control parameter, that is riser size?
So they can all change using the CMOS technology. You have one parameter at a time kind of analysis, as well as combination of parameters and the interaction between the various parameters. So it's not like only one is changing and the others are not. They're all changing, and we are looking at the combined result.
Okay, there are a couple of people that are interested in coupling CoFlow-X to stars. Now, the surface network model is thermal, so it accounts for all the heat losses and other calculations. Right now, it is not coupled to stars, but hopefully soon we are looking into it. We need to enable handling of steam in the surface network. At the moment, it is not capable of handling steam in the network, but we are looking into it, and hopefully soon we should have the capability in the future. The next question is, let's see, there's a lot of questions. I'm trying to screen and go by priority one as it's coming. Can the system be used for real-time production modeling? That's also a question from Govin. Right now, we haven't coupled it to a real-time production data gathering system. If you have the production information in a database, then that can be included into the operational design, and it can be used to calibrate and to match the data. But at the moment, there is no real-time integration in between a SCADA type of a real-time monitoring tool or a real-time data monitoring station. The other question from George is, using CoFlowX, are you able to send as constraint both flow rate and pressure from the operating point, or just send one of the variables?
So we can send both type of constraints. It can be sent as either one of them, but we are for the wells, we transfer the constraint that is the most constraining constraint, which could be pressure or rate.
Okay, the next question is from Susan, and the question is, when should I use CoFlow and when should I use CoFlowX in my IPSM modeling workflow?
So if you want to use a single system for all your modeling, reservoir, production, everything, then you use CoFlow. If you already have IMEX and GEM models created that you have worked on and are very happy with, then you just create your production system in CoFlow and couple them together using CoFlowX.
And it also depends on how important implicit versus explicit coupling is, depending on reservoir production variability, because in explicit coupling, the coupling is happening at a certain frequency. And if the reservoir deliverability is in a very, very transient state, there's fluctuations and there is oscillations happening because of new well developments and other things, or even because of the recovery process itself, you need very, very fine coupling, and implicit solutions are a lot more stable than the explicit solutions. So depending on what's happening in the network and the reservoir, you can choose either or. Just honoring the time, I think it's 9:33 a.m. here in Calgary. We are way past our allocated time, but there are several other questions by the attendees. So what we'll do is we'll get back to you individually and follow up with your questions within the next 24 hours. And we will end our webinar here with the question and answer. But I'm sure that the new software tools that Varun presented today in this webinar will make your IPSM modeling workflows easier, improve multidisciplinary collaboration, and help derive maximum value from your assets. We do offer a variety of training classes for all skill levels. If you want to attend a training on CoFlow, do contact us at info@cmgl.ca or training@cmgl.ca, and we'll be able to help you with that. We will also post a recorded presentation of today's webinar on our website within the next 24 hours. You can access our website or the webinar area using your CMGL login and a password and download it. If you have any other questions related to the presentation today, you can send us an email at sales@cmgl.ca or contact any of your sales or CMG representative in your region, and we'll be more than happy to help you out. Again, thank you for joining us on today's webinar on CoFlow and CoFlowX, modern solutions for your integrated reservoir production modeling challenges. Thank you, and hope to see you again next time.